Hey guys, it's just me, Mr. Wee. Thank you guys for joining. I do apologize, but hopefully this is actually sort of convenient for you guys. We're gonna go over chapter 8, which is just energy. Let me move my face cam over here, okay? Um, we're just gonna go through energy. It's actually a pretty simple and fairly straightforward chapter. I think you guys, it's just intuitive. It doesn't feel too like far removed from what you know already. There's only like four big things that I'm gonna go over with you guys within energy. Okay, and two of them you already kind of know, and it's on this first page. So check out this slideshow. Either you can write notes as we're going. I am gonna give you the link to this presentation so you guys can just print them out. But in all, the thing that I would actually recommend is that you don't just do nothing with the slideshow. Either you should print it out or you should take some notes, okay? Because if you end up just watching this and then just being like the presentation's online, then actually it just kind of figuratively speaking collects dust and you know it's there, but you don't like you just learn a lot better when you write things down, okay? Or you interact with the actual content, just statistically and by research. Statistically speaking, scientifically speaking, there's research to back that when you actually do something with the information, you actually do learn you retain more of the information better than rather than just passively listening. Okay, so taking notes actually really does help, or having a printout of this really helps. Okay, so there's two forms of energy. There's potential and kinetic energy. To put it simply, I know these are weird, sort of like food for one would be a really good source of potential energy because it's not in motion. Okay, it's just sitting there. It's stored energy ready to be released. So in this case, there's gravitational energy. Like if you have this over here, if I have my phone in the air and I'm about to drop it, okay, that's due to the power of gravity. Okay, there's energy from that, from the fact that it's being held in the air, and then I'm about to release it with gravity pulling it down. Okay, let me see. I know it's kind of hard to see, but electrical energy, like in your walls, ready to go at any time, is electricity. It's not yet in motion, but I could set the electricity in motion to let it get through my phone and whatnot. Okay, that's stored energy. Chemical, you can think of like rockets, like gasoline, right? And rockets, right before it's used, it's just a huge potential. Get it? It's kind of circular logic where you're using that word to describe the potential that like those chemicals have to provide energy for the rocket. Food is another sort of kind of fuel, right? For giving your biological body power to metabolize or energy to metabolize it. And also be careful when you're using these terms. Power and energy are not the same thing. We're going to describe that in just a second. Okay. So I actually don't want to mix up my words. Um, Elastic energy, like when you're about to like cock back your like a tennis racket, okay, and you're about to hit something, okay, there's a lot of potential energy waiting to actually hit that tennis ball. And the other side, there's two things. There's potential energy, and then there's kinetic energy. Kinetic energy is simply the energy that's in motion. Okay, like probably the out of all these, um, like like uh like electricity in motion, right? When the electricity is actually flowing through something, it's not just sitting in your wall waiting to be used. It's considered kinetic at this point. And another good one would be like wind, like a moving tornado would probably be like the most exaggerated example. Okay, something in motion. So two forms of energy. Okay, that's two things, and I'm going to teach you two more, but let's focus on these two first. So, what is energy? Like in general, what is it? Okay, it's simply the capacity to do work, the ability, like again, do you notice it doesn't use the word potential? But um, energy is the capacity just to do work, not the potential, but the capacity to actually do work, the capability basically to do work. Okay, so these are all the units of energy that you've seen or that there are. Okay, some of these you've probably never seen, like Newton meter, kilowatt hour. Uh, kcal. Um, The one that you've probably seen is calories. Just like when you eat things, it has calories, it has units. That's a unit of energy. But the one that's actually the most common in physics and chemistry is the joule. Okay, so that's what we're going to use. Okay, so if I could break it down, let me see. Okay, I thought, okay. So just follow my mouse cursor over here. One joule is equivalent to a Newton times a meter. And you're going to see why. A Newton meter, okay? It's like a Newton times a meter. And if you forgot, a Newton is equivalent to kilograms times meters per second over seconds squared. If you can kind of see that, okay, probably the hardest thing about physics is trying to make connections to what we've already learned. Energy is a mass times an acceleration. Okay, so um, that's actually an acceleration right there. Meters. Actually, I'm sorry. I do apologize. It's what is it? It's a let's see. I'm sorry. Newtons is a unit of force, and that is a unit of distance. So it's force times distance. So again, the unit for force is mass times acceleration. So that gives you a Newton. So like I said, these connections are really hard to make. And another way you can look at it is kg times meter squared over second squared. Okay. So here are the two different equations for kinetic energy and potential energy. I think this one's actually easier because it's a very unique one. This one's a little bit tougher because you can make a lot of connections with potential energy that can make it more confusing. Okay, kinetic energy is easy. You just take 1/2, you literally multiply 1/2 or 0.5 times whatever the mass of the object is and how fast it's going, like the measured speed, not the acceleration, but the speed, v squared. So it's 1/2 mv squared. That's like pretty simple for most students to remember. That's probably going to be the easiest formula for you to remember, okay? If you have something's mass and its velocity, you can calculate how much energy it's moving or how much energy is in motion. And the opposite, like potential energy, the easiest way to calculate that is if you take the mass. Do you know what G is? Think about what G is. I don't know. G means good. Okay. Not quite, right? G means gravity. Okay. Gravity. And H is height. So it's like a distance or a height. So think about it like this. My phone probably weighs like, I don't know, like we'll say 50 grams. We do everything in grams, by the way, okay? Or kilograms, or let's just say it's 1 kilogram. The gravity is technically, I know you want to say if gravity is a force, okay? But that's not exactly true. It's like this will exert a force because of gravity. Gravity is actually um, like let's see, like I don't want to say force, but it's like a feeling that drags you down, okay, towards the earth, and it has an acceleration, it's accelerating you towards Earth, okay, or towards this big body of Earth, okay. The gravity of Earth itself is the acceleration is 9.8 meters per second squared, okay. So that's gravity. So you multiply, like in this case, it'd be 1 kilogram times 9.8 meters per second squared. I'll show you an example in just a second. And then you measure how high it's from the floor, okay? With all those three things in mind, okay? Or actually, do you see how it's in motion? But right before it's in motion, you can calculate how much energy potentially it'll have in like when I let it go, okay? Like the energy that can be released when I let my phone go, okay? So two different things. So let's focus on, oh, and one other way that I want you to look at this, if you're for the clever students that really love the physics and the math, okay? I told you that gravity is an acceleration. Think about that. Gravity is an acceleration. Where have you seen that before? Mass times gravity or mass times acceleration, m times a. This is force, okay? In case you didn't see that, force is mass times acceleration. The unit for force is a Newton, and mass is kg. We measure everything in kg to actually fit into these um, these equations or problems that we're trying to solve, okay, in the textbook and whatnot. Force is equal to mass times acceleration. Well, what you're looking at right now is force, m times g. Another way to look at g is it's an acceleration. Earth's acceleration, or Earth's gravity is 9.8. That's a number unique to Earth. Like the sun could have a much higher gravity acceleration. Its gravity could be like 100 meters per second squared, okay? But Earth is very unique. It's 9.8. Anyways, what I'm trying to say is this mg could be substituted with ma, and because they're the same thing. And another way to look at it is potential energy. If you want to replace this whole thing, since this whole thing is equal to ma, and ma is equal to force, you could also look at potential energy as being equal to force times a height. Height is measured in meters. And let's, again, if you're not following with this, it's okay. Just know these two formulas. But if you're really into the physics here, okay, I'm going to take it one step further. Just follow me with the connections here. Ma is equal to F, okay, that's force. So PE, potential energy, is equal to force times height. Height is measured in meters. What else is measured in meters? It's distance. So you can also look at this as force times a distance, okay? That's newtons times meters. Oh, wait, what did I just say before? A unit for energy is a joule, which is equivalent. 1 joule is equivalent. 1 joule is equivalent to 1 Newton times meter. Does that make sense? Because I just said mg, which is equivalent to ma, which is equivalent to F. This part here could be replaced with F. That's force times h, or force times a distance. Okay, height is simply how, you just measure how high something is from the floor. That's a distance, isn't it? That would be measured in meters. Okay, so and the unit for force is newton, so it'd be newton times a meter. So when you calculate this, it's a newton meter. Another way that you can just another way you can call it, or another way that you can recognize a newton meter is 1 Newton meter is equal to a joule. So that's why physics can be super complicated. There's so many connections, and we're still at like the very basic level of physics. Okay, so again, let's keep looking at potential energy. So here's what it would look like in the actual units, like on a piece of paper, or a slideshow. Okay, so potential energy is equal to m times g times h. The mass is in kilograms. This gravity is unique to Earth's gravity. So this is calculating potential energy on Earth. Okay, it could be different on a different planet. Um, I do not like the unit there. It should just say 9.8 meters over second squared. Don't just forget this. I'm so sorry about that. And then height is in meters. Okay. So again, another way you could look at it is mass times gravity. Another way is just mass times acceleration. There we go. That's the unit. I like that. Should say meters over second squared. I like that way more. Okay. So here's an example. You can write this down. Let's, like, if I could have, I would have blocked all this. Let's just focus on the question here. Okay, a diver is at the top and he's waiting 10 meters away from like the pool. Okay, and he has a mass. Sorry, it reads pretty weird. A diver at the top of 10 meters at a 10-meter high diving platform has a mass of 50 kilograms. He has a mass of 50 or she has or they, okay, they have a mass of 50 kilograms. Okay, um, what is her potential energy? Okay, well, she's about to dive. Okay, so three things you have to consider. This is potential energy. She's not in motion yet, even though this picture shows that she's in motion. She's still at the top. Okay, so that's potential energy. So what do we have? We have a distance, or a height, of 10 meters. We have a mass. What's the last thing that we need right now? So sorry, we have distance and we have mass. We need one more thing. That's going to be gravity. Okay, so PE is equal to m times g times h. M is 50 kilograms. So you have to write out what you have. You have M is equal to 50 kilograms. You have G, which is always going to be the same, at least on Earth, okay? As long as you're on Earth, it's 9.8 meters over second squared. And then the distance is, or the height from which that person is, that's 10 meters. You just multiply those three numbers, 50 times 9.8. I would say that's almost about 6,000 or so. Or I mean, 600, okay? Actually, is it? Let's see. I guess I'm a little bit off here. My math's really bad. I think that's 50. So that'd almost be about 500. Okay. That's about 500, 490 or so. And then you multiply that times 10. That's about 5,000 or 4,900. So 50 times 9.8 times 10. Sorry to make this complicated. If you put that in a calculator, you get about 4,900. The units you'll have is kg times meters over second squared times m meters over second squared times m. The m's will multiply, which will give you m squared. So you have kilograms times m squared over meters per second squared. And again, if you just want to know what that is, if energy is just simply in joules, but if you take a look back at the units for energy, another type of way that you can express energy is kg times m squared over s squared. Here's another way you could look at it is kg times m squared times s to the power of -2. That just refers to this s squared. Do you see how this s squared is written? It's in a fraction. It's on the bottom. So if you write it in line, if you write it on the same line instead of having s squared written below a fraction bar, you would have to express that this to the second power is underneath a fraction. It's the denominator fraction. So that's why this is s to the power of -2. That is expressing that this s squared is below this kilograms times meters squared, like this, okay? But anyways, this and this are actually the exact same thing, okay? And that's equal to 1 joule. So 1 joule is equal to 1 kilogram times meter squared times what we call that is inverse second squared, okay? Inverse second squared. So instead of saying second squared, you say inverse second squared. Anyways, in this problem, it's 4,900 or 4,900 kilograms times meters squared over second squared, which is equivalent to 4,900 joules, okay? Here's an example of kinetic energy. We're almost done. So we're almost done with the first two things, kinetic energy and potential energy. And then we're going to go on to two new things, okay? Kinetic energy is pretty simple. Let's just say that you're 55 kilograms, you're slightly heavier this time, and you're moving at 3.87, like you're sprinting at a constant speed of 3.87 meters per second. Really simple. It's actually, the formula is 1/2 meters, or mass, I'm sorry, 1/2 mass times velocity squared. 1/2, another way you could express that is 0.5. So you take 0.5 times the mass times the velocity squared. That's why I think this is the easiest formula out of all the ones that you're learning right now. It's just 0.5 or 1/2 times, in this case, your 55 kilograms times your velocity, your 3.87 meters per second squared. Um, Actually, I don't know what the math is. Let me do the math for that. That would be, so if you're writing this down, you probably want to do you want to get the final answer, right? So it's 0.5 times 55 times 3.87. So that's about 106.4. So that would be 106.4. And let's take a look at the unit. Be careful, that would be meters over second squared. That, if when you square, or actually, I'm sorry, I did the math wrong. It's 0.5 times 55 times 3.87 squared. This would be 411, ooh, 0.9, about 411.9. The unit would be kg times, it's actually really hard to see, but it would be, if you square that, that'd be, if you can visually see it, it's, let me see if I can. Oh yeah, I got a pen here. How sweet is that? It'd be m times s meters over seconds, and you're squaring that. It's actually a lot harder than it looks. So that'd be a way that you would look at it would be like meters over seconds times meters over seconds. Okay, meters times meters would be equal to meters squared. Sorry, this is a little bit hard to see. And then the seconds on the bottom would be second squared. So it'd be, sorry, that should be to a power of 2. Okay, so meter squared over second squared. Let me see if I can clear the screen here. So if you look at it, that'd be 411 about 9, and that's kg. And then I just told you that this is meters second squared over meter squared over second squared. 411.9 kg m squared s squared over s squared. And if another way you could look at that is, sorry if you guys can see this, it'd be 411.9. That's like the same thing here. I know it's written a little bit differently, but it's kg times m squared over s squared. But another way you could see this is that's equivalent to joules. So all this is equal to 1 joule. 1 joule. So if you have 411.9 kg m squared over s squared, another way you could look at it is 411.9. And instead of all this, you just put joules. Okay, so instead of all this, whoops. Okay, you can just put joules. Okay. Okay, let's clear that screen. Let's move back. Okay, so those are kinetic and potential energy. Again, another way you can look at it, there's a ball that's right at the top of a hill. We haven't released it yet. It has like almost no kinetic energy, but when you release it, or I'm sorry, right before you release it, it has a huge amount of potential energy. Okay, so the ball is like right here. I drop the ball, and then it has to be the same amount of total energy. So, like the fact that you had 0 KE, in this case, your kinetic energy goes up because it's now in motion, but you're losing potential energy. Does that make sense? So as one goes up, like your kinetic energy goes up, the potential energy, the stored energy that you had is being used up because it's in motion now. Then down here, it's like a higher amount of kinetic energy because it's really in motion now. It's like going down the hill fast. The potential energy is actually really low now. Now, at this point, the ball is like 100% in motion. There's almost no potential energy. There's no energy just being stored. It's like completely in motion. So all that energy that was potential is now completely like kinetic energy. Then up here, the kinetic energy is low because when it's going up the hill, it's slowing down and it's becoming stored energy. Okay. And potential energy is going higher. And as you get back to the highest point of this hill, again, the other side of the hill, you're no longer in motion. So kinetic energy is really low, and then potential energy is really high. Okay. It's crazy stuff, right? Okay, so now we're gonna move on to two new things. Okay, it's like a hip hop song. Okay, like power, power. Okay, I don't know what I'm saying, but it's like a Kanye West song, I think. He has a song called Power. Okay, despite your opinions about that person and their opinions. Okay, still a pretty talented artist. Sorry to kind of. Hopefully, by the time someone's listening to this or watching this recording, um, the reference that I made to that artist is not irrelevant. And you're like, I still know who that is. I hate him or I love him, but I still know who he is, or else I'm gonna feel really old. Okay, I don't want to feel old. Okay, so I talked about kinetic energy and potential energy. Okay, now I told you I was going to talk about two more things. So just like how I described kinetic and potential energy, I'm going to describe these two things, and they are not the same: work and power. Okay, so people completely interchange energy and power. They're not the same thing, but The reason why people get them mixed up all the time is because they are related. They are totally related, okay? So let's take a look. Work and power. What's the difference? How would you describe it? I mean, how would you describe it? I would say power is like power is money, money is time. I'm kidding. It's not that, okay? Work, I think we all can relate to work, okay? But what is it in a physical sense, okay? Work represents the amount of energy being transferred. So you have to take two things into account, the energy being used, okay? Just like what we were talking about before, energy and distance. So it's like now we're looking at energy carried over a distance. Like if we looked at how far this guy pushed this mowing thing, okay? Like if we took into account how far he pushed it, the energy that he's using and how far he's pushing it along somewhere, that's how much work he's putting in. Okay. Um, and then power represents how fast that energy that he's putting into something is transferred. I'm going to say it one more time. So, sorry, this is blocking it. So, work on the left hand side, okay, work on the left hand side is the energy, the amount of energy being transferred, the amount. Power means how fast the energy is being transferred. Work is how the amount of energy being transferred, and that you have to take into like the distance, like the energy that that person's putting in and the distance that the energy is like being used. And then power is just how fast in time, like how many seconds does it take for this person to burn up that energy. Okay, so I'm going to say again, work is done on so you look at work, how much work is done on something when a force causes a displacement, or basically like a displacement is like a distance. It's um I'm sorry, it's not energy, it's force. I apologize. I said energy. You have to take into account two things, energy and distance. I do apologize. It's force and distance. Okay, so it's how much force you're putting in into something. That's a little bit different. Okay, like how is it different? Um, I told you that. Whoops. So we have to make a lot of connections here. Okay. So again, like energy or so energy is technically um m times g times h, which is mg or is equivalent to ma, which is basically force. Okay, that's it's force times times h, force times h, or another way you could look at h is distance. So you know what? Actually, I think I was completely wrong. Work is the same thing. If you're thinking about the formulas, the formula for work is force times distance. That's actually technically the same thing as potential energy. I completely forgot that connection. At least to tell you guys, it's not like I completely didn't know this. Like I did look at the slides. I was like, okay, they're the same thing, but I was telling myself not to mention it to you guys because I didn't want to confuse you guys. And hopefully I'm not confusing you guys. It's still four different things. Okay, it's kinetic energy, potential energy, uh, power, or I'm sorry, work, and then power. Those are the four things I'm teaching you today. It just happens to be that potential energy and work are actually numerically speaking, if you do calculations, they're actually the same thing. Um, so what was I saying? It's a force times, so it's m times g or m times a, okay, which is equivalent to force, and a potential energy is force times h. So yeah, if I could draw that, so this is all equal to ma. And if you think about that, that's equal to force. And another way that you could look at h is it's a distance. So potential energy, another way you could look at it is force times a distance, okay? And what is the equation for work? It's just how much force you're putting in over a distance or how far you're displacing something. So it's actually sort of the same thing. It is the same thing. Power, I think, is much more unique and easy to understand. That's you take the amount of work you put in and you divide it by the time. So how fast you're doing the work. Okay. the rate at which work or the rate at how fast the energy is. I just said work. I just said, remember, work is, and I just said it's equivalent to potential energy. M times G times H. Okay, these two things are actually the same thing because this over here, mg, is actually equivalent to work. And then height is a distance, basically. It's the same unit. Like if I said the height of something is 50 meters, then that's the distance from the ground. It's the same thing. So instead of h, that would just say force times lowercase d, okay? F times d, okay? So they're actually the same thing. So work and potential energy are the same thing. So you could also look at power. P for power, not PE, but P for just power is also equal to potential energy divided by time, or energy over time, okay? So that's why I said power represents how fast the energy was transferred. It's also PE divided by time, or work divided by time, okay? But let's keep it simple. Wait, how do I clear this? Oh, okay. So instead of trying to make the connections, let me just say again, kinetic energy is 1/2 mv squared. PE is just m times g times h. Okay, if you can't make all the connections, it's just I'm the teacher, so I'm supposed to make the connection so you can see them at least. Work is equal to F times D, and then power is equal to work divided by time. Okay, so if you can't make the connections, just know that those are the four formulas. So in terms of work, let me give you an example. A child uses 25 newtons of force in order to move a toy car a distance. So he's putting in a force of 25 newtons of force, and he's pushing a toy car. Okay. Um, and you see kids doing that all the time. So what do? It's just, again, work is equal to force times time, or distance. And that's easy. It's just you take 25 newtons and you multiply that to 5 meters. And that should be 125 Newton meters. Okay, so you could leave it like that, but just remember that a Newton meter. So connections time. I know you guys don't like making connections. Some of you guys actually might be really enjoying this. A Newton meter is equivalent to a joule. So the answer for this could also be written as, sorry, that's an arrow. 125 joules, which I just said that makes sense because I was saying earlier that work is equal to potential energy. It's the same sort of idea. Mg, which is equivalent to force, and then the distance is equivalent to height. So energy is always calculated in joules, right? So it totally makes sense, all these connections. Okay. Let's take another one, another example I think is really easy to understand when you see it. It's this person that was here. He's pushing this crate, and he put in 20 newtons of work. Okay, there's a lot of information here, but let's just, um, so there's a lot of information that might confuse you, okay? This person put in 20 newtons of work. The crate is 50 kilograms. He moved it 15 meters. There's 3 bits of information, but remember, for work, if you're asking for work, you only need 2 things: the amount of force that you put in and how far you pushed it, okay? How far you displaced it. So you got the amount of force that this person puts into pushing something, and then the distance he pushed it. That's all you need. You don't need that 50 kilograms. That's put there to confuse you, okay? But you only need the force that this person puts in and how far he's traveling. So all you got to do is you take, actually, you don't look at this. So this is actually not important. Only this and this are important. So you take 20 newtons times 15 meters. 20. So this is what it is. 20 newtons times 15 meters. You get 300. You should get 300. It would be Newton times meters. But remember, I told you a Newton meter is equivalent to a joule. So 300 Newton meters or 300 joules. Okay, pretty simple stuff. Another example of work is if you can't see it. So this has no visual. Lifting a 2 kilograms. So we're looking at you lifting a rock off the ground, and it has nothing to do with you. I don't see any kilograms about you. You're talking about just the object, okay? 2 kilograms of rock off the ground, and you put it at a table. So you're putting a rock up and onto a table. I know this doesn't look like it, but this is a table. So there's a distance here that you're putting this table. It's 1.3 meters. So what do we want? We want work is equal to force. I mean, the work's right here, but I would just show get it, the work for work. Okay, work is equal to force times D. But remember, you can break down force as equal to M times acceleration times D. Oh my God, you're getting mad. You get it? So it would be mass times acceleration times D. So we have the distance, which is 1.3. That's what we got. We got the distance is 1.3 for sure. We actually don't have the force. It doesn't give you the force right away, but we can calculate it. You just take, we do have a mass, so that's good. We want to calculate the force though of that. We don't want to just have the mass. So what you take is you take 2.3 kilograms and you multiply it to the acceleration of Earth, which is a gravity, which is 9.8 meters per second squared. Okay, this is getting really messy. I'm going to clear it because it's right here. That's the 2.3 kilograms. So that's where he's getting this. So work times is equal to force times distance. There's the distance, which is, sorry, so here will become this, okay? That's what this is trying to show you. Whoops, that's supposed to be an arrow, okay? But in order to get F, this is what you have to do. You take the mass and you multiply it times the acceleration, which is 2.3 kilograms times 9.8 meters per second squared. So you would have gone, so this is a mass, kg times 9.8. So this should have said kg times meters per second squared. That's not the same as kilograms meters squared over second squared. It's just kilograms. This is not, so this is not energy. What do I mean by that? I just said that energy up here was kilograms meter times meter squared over second squared. What we were doing just now is kilograms meters over second squared. I don't have a squared meter here. Okay, so anyways, I'm going to go back. That's why physics is so tricky. Okay, anyways, 2.3 times 9.8, that's about 22.5 newtons. That's the force. And another way, instead of saying newtons, was where did the newton come from? Well, the 2.3 kilograms times 9.8 meters over second squared, you have kg meters over second squared, but that's equivalent to just this, n. So you don't have to write this. Okay, so it's 22.54 newtons. Then to calculate all the work, you take the force and you multiply it to the height or the distance, which is 1.3. And that's what's going on right here. This you put in here, 22.5 times 1.3, and you get 20. So that would be, this is newtons, and this is 1.3 meters. So the actual answer, if you did the math, 22.5 times 1.3, it's just this number, 29.302. But you could have wrote it as, whoops, ugh, what am I doing here? This could have been 29.3, about 29.3. And then the unit was newtons times meters. But a Newton meter is so a Newton meter is equal to a joule. So that's why on this work here, hopefully this is like really easy for some of you guys. Like, oh my god, like you don't have to explain every little step, Mr. Wee. If you're at that point, that means you're really getting it, okay? But if you're not getting it, it's okay. Just rewind this a lot and just keep working at it in the physics homework. That'd be 29.3. Instead of joules, it'd be Newton times meters, okay? It's the same thing. Newton meters and joule is the same thing, okay? Okay. And there's one more example. So that was all about work. That was all about work, baby, right? We're going to do power, which I think is really easy, okay? A machine does 30 joules of work. So, like I said, work is just another form of, like, it is technically related to energy. It is just potential energy or energy. But let's say you did 30 joules of work in 10 seconds. It's really simple. What do you do? Well, power is equal to work divided by time. You just take 30 joules and you divide it by 10 seconds. And then you'll get 30 divided by 10 is just 3. And then joules over seconds. And like all physics, there has to be an easier or another conversion or another unit for joules over seconds. If you can't tell by now, you're going to have to just get used to being like, this unit is equal to this unit and this unit is equal to this. I know um, it's really annoying, okay, but that's what makes physics, okay? And if you know any of it, you are partly a physicist, okay? And the general point of education is for everybody to have been exposed to at least the same vocabulary of education. So the hope is maybe we can have some conversation about it, or you exercise your brain to critically think in ways it doesn't want to necessarily think on its own. Okay. So that way, the hope is when you have a conversation with someone else and you're trying to better society or humanity, okay, or your collective society that you choose to be within, okay, you want to be a contributing member, you somewhat have a basis for understanding. So that's what this physics is. You might not get all of it, okay? But for one, you're exercising your brain to think in a critically different way, okay? Or you're getting your brain to critically think in a different way. And also, the hope is when you're talking about science, you remember some science and calculations. You don't remember the details, but when you talk to someone else about something, like a law or something like that, or like why did that building collapse? You're talking about something in real life, and that's part of your job or something, or you're trying to help. Um, a person might mention some calculations, and you might not understand it, but you understand the significance of the calculation that person's putting in. Do you see what I'm saying? So, my apologies. I'm kind of going off the deep end of philosophy here, but um, that's why it's important for you to actually be exposed to physics. You don't have to understand this 100%, okay? But I do want you to be exposed to it, so you're part of the conversation. You're not completely left out when people talk about this kind of stuff, okay? You know what engineering is. It's all this physics stuff that people have to take in consideration, okay? That's what's really important. So, anyways, joules over seconds. All that from units. I don't know why I got so crazy. Okay, so it's 3 joules over seconds. What is a joule over a second? You might have heard this before. It's a watt. So whoops. So 1 W or a dub. I think that's a term right now in 2022 for sports. Namely, I've heard it in like the context and culture of basketball. If you get a dub, I think that means you got to win. Well, in chemistry or in physics, a W isn't quite a win, okay? Or maybe it is for some of you, okay? It's a watt, okay? So 1 watt is equal to 1 joule over seconds. You're talking about something's power. So you've heard that. That's why it's really easy to get this mixed up. You're like, oh, how much energy, or what are we looking at? Like, what's the power right now? It's like, oh, it's like 50 watt. You ever heard of that? It's not the same as energy. Um, but it's really similar. I told you work is actually equivalent to energy. So, but you're talking about energy in time, like how fast energy. So when you're talking about power in a room, you're talking about how fast the energy is moving in the room, like how fast the electricity is moving around in the room. If it's moving really fast, you have to be careful. Like you can have a megawatt, you can have tons of watts. Okay. So what that's expressing isn't just energy, but how fast the energy is moving. So again, it's joules over seconds. How fast? It's like meters per second. How fast are you moving in meters? Well, you can talk about energy. How fast energy is moving per second. Okay, that's a watt. Okay, so again, over here, this was 30 joules of work in 10 seconds. That's 3 joules per second. That is 3 watts. Okay, things can get much higher. All right, guys, that's actually all I have for you guys. I'm going to stop here. So, again, summary: 4 things you learned. 2 of them you already knew. It was just 2 forms of energy: potential and kinetic energy. Then you learned about work, which technically is related. It's just work is actually energy. It's just maybe seen in a different way when we talk about it. And the last thing is power. That is something new. That's how fast energy or work is done in time. Okay, work divided by time. Okay, what you have right here. 4 things that you just learned. Okay, if we can keep it simple. And I just gave you some experience in showing you how to do some work. Oh, I mean, horrible. I should not use it as a pun. I just showed you how to do some of the problems, like numerical problems, for these 4 types of different formulas that we just learned. Okay, guys, that's all I got. Okay, you guys have a good night. Bye.